So we're doing a quick overview of what we discussed in this chapter, chapter 11. So prior to this chapter, we talked about the the three atomic models. We only discussed three significant atomic models. So these are the models where scientists describe what they think the atom is and what is inside the atom. So we have Dalton's atomic theory, I call it DAT. He says the atom is round, and he says there's nothing inside the atom. He said 5 more things, so make sure you know those 5 things, right? Everything that Dalton said about the atom, and this was covered in chapter 4. And then after that, we discussed J.J. Thomson. J.J. Thomson was the one who described the plum pudding model, also in chapter 4, where he talks about the atom looking like a plum pudding model. Now, we can't technically relate to a plum pudding because we don't eat plum puddings, but we eat muffins. And the plum pudding looks like a muffin, where instead of it being the muffin shape, it's round. And inside you have, in the place of plums, you have negative electrons. So these little circles here representing electrons, and then the inside or the interior of the plum pudding is supposed to be positive charge. So J.J. Thomson talks about a neutral atom where you have these plum pieces that are technically electrons. Because he did notice that, unlike what Dalton said, that they were electrons inside the atom. And then JJ had a best friend, Rutherford. Well, they were close friends. I just call them best friend, his BFF. Rutherford, sometimes called Rutherford. I like saying Rutherford. He's JJ's ex-best friend because Rutherford set out to help his friend JJ Thomson to prove his model. But he goes out there, does experiment. The experiment is called the gold leaf foil experiment. And once again, this is discussed in chapter 4, where he discovered his friend JJ is wrong. Now, what do you do when you do your work publicly? You publish your work, and then his goal was to help his friend, but now he discovered his friend is wrong. And mind you, all this work is being published, released to the public, and people are reading this. Your family's reading this, your coworkers are reading this, and then they publicly find out you are wrong, right? But it's not really a rule, but it's an expectation in science. Even if you discover you're wrong, you own up to your mistakes and you publish the truth. So when Rutherford discovered JJ was wrong, he published his own model. Now his model is called the nuclear model. So the way I learned this and the way I remember this to kind of dramatize it a little to make it more interesting for my taste, it's kind of like when people are in a group, right? Singers are in a group, and then one of the singers goes out and releases their own album, and then they are the only ones that get the credit, the rest of the group doesn't get the credit. Or they used to be a group, then they break off and one person goes off on their own, kind of like what Beyonce did with the other group members. She went on her own and got even bigger than them. That's kind of how I feel like the energy is here. They used to work together. Not only were they friends, Rutherford was JJ's student. So they're working together in the same lab. Rutherford is like, I want to go ahead. He did him wrong. Yeah, you know what I'm saying? He did him wrong. But he has to publish the truth. What do you do? So he publishes the truth and says, no, the whole interior of the atom is not positive. Just the center, the nucleus, right? That's the only part that's positive. And then the whole interior of the atom, except for the nucleus, is actually negative. So it's kind of the opposite of what J.J. Thomson said, right? So chapter 4 kind of covers this part here. I mean, there are more details into it. When I'm saying chapter 4 here, I mean chapter 5. It's the one previous to this. Chapter 4 talks about gas laws. I forgot. In your book, chapter 4 is gas law. Chapter 5. Chapter 11 then picks up where we left off. Chapter 11, we're discussing 2 things. We're discussing Bohr's model. And Bohr is a scientist who came up with a model, the planetary model. The planetary model is the most popular one. That's the one we see on TV, Jimmy Neutron, Big Bang Theory. When you see Hollywood showing the atom, they tend to show this atomic model where you have the nucleus in the center, and then you have the electrons moving around. They're orbiting around the nucleus. That's the planetary model. Then when it comes to the quantum mechanical model, the one we see right here, the quantum mechanical model, that one is complicated. People barely talk about that. People in deep chemistry discuss the quantum mechanical model. So what I'm going to do here is actually Google. Since I've already gone over this, watch the previous videos to get the details. I'm going to Google right here. And then we'll Google the quantum mechanical model to see what's out there. If I can spell this right. Quantum mechanical. Scientists don't even try to draw this because it's so complex. Okay. Okay. There's this picture right here. Actually, I would say this one here is trying to show you what the inside of the atom looks like. It's very complicated, so it's not bad, but it's not showing you the big picture. This one right here that they show the quantum mechanical model, this is technically Bohr's model. Bohr's model to the left, right? G and neutron, where you have the electrons orbiting around. And then this one here is the quantum mechanical model. So I would say the best depiction of it is this one here. This picture. And this is not even showing you everything inside the atom. There is a nucleus here, and then inside the nucleus there's a bunch of different shapes. Some of them are spherical, like what Bohr saw. Some of them are spherical, like this is a small sphere, a bigger sphere, and then it keeps going bigger and bigger and bigger. Some of them look like these balloon structures right here, like a figure eight or what looks like a flower, and that keeps getting bigger and bigger and bigger. So it gets complicated. And some scientists have tried to show, so right here, you have the quantum mechanical model here, and then to its right, you have Bohr's model. So you can see how different the models are, right? What Bohr saw, Bohr only saw the circular orbitals, well, he called them orbits, where the electrons were. The scientists here were able to see more and realize that the structures inside the atoms were not clear cut like what Bohr said. Everything wasn't round. So it does get complicated. And as I said, different scientists try to present the different images. Oh, here. So this picture I like because it's showing you a much better presentation. So this one here, what is this? This shows you the different levels, right? Which I can't even show you this. How do I make this bigger? Hold on. I just make this part bigger. I don't want to go into this. Okay. No, X. Okay, so hopefully you can see here, right? Let me make this slightly smaller. I don't want to log in. This Pinterest, I guess. They're gonna have me. So you can see right here, right? Dalton's model. You have Thomson, J.J. Thomson. You have Rutherford's model, Bohr's model, then you have this one right here. Now, Rutherford's model, usually they just kind of show you the nucleus in the middle and they don't really show you this part much right here. But then you have the quantum mechanical model right here. Anyway, you get the idea. So I want to go back and look at, yeah, I'm going to go back and look at what we're studying right now. So we're back here. The quantum mechanical model. So understanding the complexities. Yeah, ads, tell me about it. They're trying to get you to sign up for stuff. So you see here, you have a nucleus, you have balloons around here, bubbles. Everything gets so complicated in this structure right here. So scientists do understand the quantum mechanical model. Inside the atom, we have these bubbles, and these bubbles are probability maps. They're bubbles, but they're showing you the location where scientists last found the electrons. Just like we have the map of Texas showing you where Texas is, we have bubbles in here, and these bubbles are showing you where the electron is, and those bubbles are called orbitals. So as we go through here, you can see, I'm just going to skim over the details. You can see how we talked about the different parts of the electron, saying the electron does have two natures. I started off here talking about humans and the two natures that humans have. You can say, well, three parts of the human, the body, soul, and the spirit. And then just like humans have a body, soul, and a spirit, you have electrons having two natures. And that nature will be a particle nature and a wave nature. So since I'm giving you guys just a big picture of this, the wave nature ultimately is the part that gives us all the wireless technology in the application sense. Okay? So when I was in school, right, I understood the particle nature because it was more straightforward. This is when you have the wire technology. And then this part here is more tangible. So when you think about things you can see, things you can touch, you can experience, you can interact with, we can understand that even gases will fall under the particle nature of the electrons. The wave nature, though, things we can't see, we can't even touch because they're not physically like the particle nature. Here, when the electron is behaving as a particle, it has mass, it has velocity, it has a speed, and it has dimension, right? So I'll say it has a size. When we're looking at electrons having a wave nature, here we're saying that it can release light. It can also respond to light. So there's so many different characteristics that the electron has, and it has a wavelength. It behaves like a wave. Okay, so the electron has two natures. So since scientists did not understand this nature very well, it was harder for them to understand because first of all, they weren't even aware the electrons had a wave nature. They knew the electrons had a particle nature because they were able to measure that in the lab easily. Okay, as time went by, they realized no, there was more to the electron. It had a wave nature. For them to understand that, they went ahead and studied light. So that's what we did right here. As we are studying different behaviors of light, we were then giving that same behavior to the electron. So we go through all the details, watch the video, make sure you know the difference between the kinds of waves. We talk about the electromagnetic spectrum and the different kinds of light waves we have, the different colors of light, the different waves we see in the electromagnetic spectrum. We also say, just like this spectrum has different waves of light, the electrons can release different waves. Some of them are visible to where we can see, some of them are invisible to where we cannot see. Okay, so the electron is able to release some of these waves right here, just like the ones we see in the electromagnetic spectrum. So we went ahead and talked about the different wave behavior. This is showing you how white light produced by the element tungsten. The white light is actually composed of different colored lights. So we talked about Roy J. Biv. When you have red light, orange light, yellow light, green light, blue light, indigo light, and violet light, and you combine all these together, they make white light. Now remember, I'm skipping the details because that took me 3 lessons, 4.5 hours to go over all of this. I can't do that in the same amount of time. So just go through the other parts and then, get all the details. I'm just giving you a snapshot. So while the metal tungsten can produce white light, and if you take white light and split it into the different components, you realize white light is made up of all of these different colors of light. And please notice, this reminds me of tie-dye, right? Where the colors bleed into each other. So the blue is bleeding into the green, into the yellow, eventually to the red. You're not seeing a separation. They call this a continuous spectra. So I defined that in the previous slide or the previous PowerPoint and the previous presentation. Continuous spectra looks more tie-dye of all the colors that are shown in that light versus the line spectra. The line spectra, you can see how the lines or the colors are not bleeding into each other. It's more distinct. So you have a color right here, more like a blue violet. Then you have from color to area of darkness to the blue green to area of darkness to the green area of darkness, a huge area of darkness right here. Then finally the red. Okay, so this is called the line spectra. because the spectra looks like a line. There's no tie-dye here where the colors bleed into each other. They are more distinct. The term they use here to describe distinct is discrete. In English, discrete means like hush hush, keep it hush hush, quiet. In chemistry, discrete means distinct, like they're not, they're clear cut, right? Where the blue is clear cut, where the red is clear cut. They're not bleeding into each other. So you have discrete lines. How do you get these lines? This is actually showing you hydrogen. If you take the element hydrogen, which is actually a gas in a gas form, and pump it into this spectral tube, this gas discharge tube, it produces a purple light. So if we were on campus, we would have seen this, and this would have been a purple light. Well, we always want to know what are the primary colors, or what are the colors that we know of that produce this light. So you take that light through the prism, well, eventually through the prism. You concentrate it, that way it's really focused, right? And then take it to the prism. The prism has a role to separate the color light that we see to produce the individual light that make up the purple light we see. Up here, the prism showed us, right, after separating the colors, that white light is made up of all of these colors mixed together. Down here, the prism is showing us that what we are seeing as purple light is actually a combination of these four colors: violet, blue, green, and red. When you mix them all together, you get the purple light. At some point, I discussed this last time, that elements, all the elements in the periodic table had their own spectra they produce, their own distinct spectra. So this one that we're seeing here is for hydrogen, and only hydrogen can produce these four lines this way. So this is for hydrogen only. There's no other element that can produce these four distinct lines in this particular spot, okay? Scientists, especially chemists, have a habit. If there is a behavior they see in a particular element, it's almost like a light bulb switches on, like, okay, since this element is the only element that does this, we're going to use this behavior as an identifier, right? With humans, you don't do that. They say, oh, that's stereotyping. Don't assume because I'm this way, I'm going to behave this way. But with elements, it's okay. So the next time we're doing something, if we see these four lines and they say some gas element produce these four lines, we can say, oh, that element for sure is hydrogen. Why? Only hydrogen produces these four lights, these four bands in those specific locations. Okay, so we can kind of work backwards, extrapolate backwards, and say, since hydrogen produced this and only hydrogen can do that, when we see this configuration here, we blame it on, or we attach it to hydrogen. Okay, so scientists use that kind of line spectra as a fingerprint. So they just show you that, okay, just to kind of be clear, hydrogen produces those four bands in specific locations. Then this is the one produced by mercury. Please notice the blues are always in the blue position, and then this is the one produced by neon. Okay, so of course I've kind of been curious because there's an application to this. You know, neon symbols, neon lights, when you go to a very busy place at night where they have beautiful colors of lights out there, they're usually neon signs, right? They call them neon signs. In my recollection, neon signs have different colors. They're not the same color, right? So, well, then how they get the different colors? Well, I mean, that's where engineering comes in. Chemistry, the best we can do. So in chemistry, we can tell you how the colors are made. In chemistry, we show how colors are made. So this is where the engineers come in. And if I could do it over again, this is the thing, you know, I'm kind of caught because I like explaining the why. I like demystifying things. That's why I like chemistry, right? I like watching murder mysteries, who done it, who did what, and trying to figure out who the culprit is. So I enjoy chemistry. But I also like practical things. So this is where the engineer comes in. While we can tell you how the colors are made and where they're coming from, when the engineering comes in, the engineer tells us how to manipulate and use it. So we're like, okay, we can make what is it called? Yeah, we can make we can make colors from elements. But then what do we use it for? I don't know. Engineer comes in and they're like, oh, July 4th. Now, that's an oversimplification of their role, but when they show us how to use it, fast forward, we have July 4th. And on July 4th, scientists take chemicals that are in powder form, packed inside the little firework things, they light them up, electrons do their thing, and we get a bunch of different colors coming out in beautiful shapes when we have fireworks, right? Now, there is some engineering there, there is some business involved there. So, at some point, I was telling my students that in reality, even though when you go to college, you learn these classes separately, outside of college, they don't work separately. If you have a company and your company is making fireworks, you have to hire a chemist if necessary. But actually, you don't have to hire a chemist because we already know how to make the light, right? You can hire an engineer who has to know some chemistry. You hire a business person, hire a person to put it all together. So, all of these areas that you guys are learning in school is working together ultimately to make this chemistry stuff useful. Okay. So, back to Bohr. Bohr was a scientist who explained the line spectra. Up until that point, nobody knew where these colors were coming from. People knew electrons were in the atom, but they didn't know how the electrons were behaving to produce light. So, remember his atomic model? Right here, I showed you guys how the electrons are at specific orbits according to Bohr, and you have orbits that have lower energy, like we have right here, 100 joules. So I just showed you have a nucleus in the middle here, you have lower energy, 100 joules, next level 200, 300, 400 energy level, and different electrons were able to travel differently. So electrons usually have homes, according to Bohr. And the home where you found the electron is called its ground state. So this is where you would normally find the electron, its ground state. Kind of like when you're home, that's your home. So this is the electron's home. Electron's home. So according to Bohr, sometimes energy comes from outside, such as humans. If we light a chemical or maybe pass electricity, energy will come from outside and the energy will zap the electron, or the electron will absorb the energy. And when the electron absorbs the electron is able to go to a higher energy level. So what I have failed to mention, which I mentioned in the previous lesson, was that when the electron is in its home state, the electron has to have an energy that matches the orbital. So right now I'm showing you this electron right here. I'm going to color it blue. This electron in its home state has to have 100 joules. Why? Because that orbital has an energy of 100 joules. So the electron has to have an energy that matches the orbital. And then somehow stuff happens, the electron absorbs the energy, and then it gets to jump. So it depends on how much energy it absorbs, right? On the other video, I only showed one transition. It went from here to here. So if the electron moves to energy level 4, where the energy is 400 joules, that means the electron gained 300 joules, so that its new position when it's right here, it's still electron 1, is now at 400 joules total. So depending on how much energy the electron gains, it goes to that fourth level, where the fourth level has 400 joules of energy. So it's kind of like a game, right? Electron absorbs energy. Then the question is, how much energy does it absorb? What is its new energy? If the energy is 400, it jumps to this level. If the energy is 300, it jumps to this level, because this is level with 300 energy of joules, right? If the energy is 200, it jumps to just this level. So the electron will have to move to a new orbit so the electron energy matches the orbit energy. Since that was not its original energy, they call this the excited state. So when I was learning this, remember, I usually tell you guys this, I realized I call it a selfish learner. I'm not ashamed of it. I own it, okay? Because it helps me learn. I own it. I'm a selfish learner. When I was learning chemistry, we started learning this in middle school. So we're talking at the age of 13, 12, 13. You're learning this stuff. And the teacher is saying the talking, and you're like, I don't know what's going on, but the guy next to me is cute. Totally distracted, right? Now, for me, what helped was the teacher was young and hip. So I'm like, okay, I don't know what he's talking about. He wasn't bad looking either, but he was young and hip and he was talking about chemistry. I'm like, I have no idea what he's saying, but I'm to it because he's into it, right? So I'm listening to what he's saying and excited, gonna say, yeah, sure, whatever. But I started to inject myself into the lesson, and then all of a sudden it started to make more sense. So instead of talking about an electron out there somewhere, I became the electron. And I'm trying to think about what's happening. So I noticed, for me personally, when I drink coffee, I get super excited, right? You have more energy, you're excited. Now, so in this analogy here, I will be the electron. The coffee will be the outside source of energy. So I drink coffee. Depending on how much caffeine in there, I can be super excited or mediumly excited. Now, and once I drink the coffee, I enter into the excited state. And I'm extra chatty. Yes, more extra than this. Extra chatty, so energetic, but that state doesn't last forever, right? At some point, it wears off, you get tired, and then you kind of go back to where you normally are as far as your energy state is. So I use that to help me connect with what's happening to the electron. As the electron gets an outside source of energy, it actually has many places to go. It can go here, it can go here, it can go here, right? Can go here, here, and here, depending on how much energy it has. The new level the electron is in has to match the electron's energy. The excited state is temporary, so the electron has to go home eventually. When the electron goes home, though, it has to lose the energy it gains. So when it goes back home, it has to lose all the 300 joules of energy it gained. So I'm showing you that right here. And then it goes back home, and now it's at 100 joules again. So it's kind of like a game, right? And then it starts over and over again. So when you're seeing a continuous source of light, what you're having is thousands. I mean, Avogadro's number, not just thousand, but thousands and thousands, 6.022 times 10 power 23 amounts of atoms and the electrons inside the atoms, jumping up and down, jumping up and down, jumping up and down. And all we're seeing on the outside is light, if we can see light. Okay? So recognize as the energy level increases, so does the value of n, and then you go to a higher and higher and higher orbit level. Okay? So I showed you here, orbit energy equal electron energy. So remember, you have the different orbits and you have different electrons. Over here, I showed you guys before, there are some electrons whose ground state is just energy level 4. That's their natural home state. So they can only travel further up, right? So you only have electrons gaining energy to go to a higher energy level, not the other way around, okay? Okay. So this slide here, this is a detail I went over that already, so I won't even go into that, but it shows you right here. And this picture, they're showing the second half. Once the electron went to the higher energy level, now they're coming back home. This is the ground state of F electron, the ground state of E electron. This is the ground state of D electron. After they absorb energy, they're now heading back home and they're releasing this energy. So when you do your experiment, the one about determination of quantum numbers, I think, right, you'll be going over this here and you'll be working with hydrogen. So you get to see the different transitions of the electrons with hydrogen. So I went through all this right here. Feel free to look at that. This is showing you once again, electron at the lowest energy level possible. It absorbs energy right here. The energy came from an outside source. The electron got so excited, yay, and then jumped up there and sitting here. As long it has this new energy, it stays up there. Excited state does not last forever, so the electron has to come back home. When it comes back home, it has to lose the energy. So they try to use the exact same picture to illustrate the amount of energy gained ends up being the amount of energy lost as the electron comes back home. Okay? Please notice it takes a lot of energy to go from here to here, but from here to here is lesser energy. And as you go up, the amount of energy required to go to the next energy level is smaller and smaller and smaller. I don't think I mentioned this before, but since I'm here right now, I'm mentioning that. Okay. Then after doing all that, you see how I reviewed here? After doing all that, I was showing you the quantum mechanical model. It is complicated, but in the quantum mechanical model, we're now talking about the orbital. The orbital is a 3D region around the nucleus where the electron is found. So when you think about a map, right? The maps we have, old school maps, at some point, okay, so at some point, it's okay, I'll just share this. At some point, I had a job when I first graduated, this is like undergrad, where I had to use a map. I was broke, so I couldn't afford a GPS. And I didn't have a smartphone, I had a regular phone. And so I got a paper map. I didn't know how to use that one very well, so you can imagine, man, I learned a lot from that. The paper map is a 2D map, right? And you're on the map and they're telling you go from here to here, so you have to figure out what road to take. Turn right. There was no GPS, so I was my own Siri, right? Go from here to here. But you get the idea. The map is a region on the ground that shows you where places are. Like you have Dallas map. I don't think this is what Dallas looks like. You have a 2D region. So the idea is with a planetary model, Bohr's model, the planetary model, he had these orbits that were round. So they weren't even maps, they were more like just paths. You have a nucleus, and then there were paths around the nucleus. So it's kind of like a map, but to me, I feel like it's more like a highway. So a map, but that's showing you a highway, right? So you have a circular highway around a central point, and the orbits, according to Bohr, to me look more like highways. So you find the electrons on those orbits. So if you know the electron is here now, you can predict later on it'll be somewhere here. According to Bohr, he made it sound as though there was a very specific spot where the electron is. And according to him, if the electron is absorbing energy to go anywhere else, you find it on its ground state right here. Right? And then if the electron jumps to the next energy level is right here, now you see it right here. Or you can have electrons who have this natural ground state, looking more like a path, like a highway. But in the 3D model of the quantum mechanical model, we're saying no, electrons are not stuck to a highway. They can actually float. So this kind of reminds me a little bit maybe of Jetsons versus this. The electron is not stuck to a highway on the ground, or the way Bohr is talking about this. The electron is actually in a 3D region around the nucleus. So instead of a circle, we now have a sphere. And inside that sphere is where you find the electron. It could be here, it could be here, it could be here or here, but it's a 3D space, this whole region versus a path where you find the electron. So we have 3D region versus 2D region. And the electron can be found anywhere in there. And then this region is even bigger, and the electron is found anywhere in here. Okay? So in the new quantum mechanical model, you have the principal energy level, just like with Bohr's model, and this tells you whether the electron is on the smallest energy level, close to the nucleus, or further away. So we went through all of this part here, and I showed you how to use the periodic table to tell the energy level of the electron. So I think I talked about this right here. So I've already gone through and labeled all of this. Depending on the element you're working with, for the most part for you guys, I'll just tell you the electron, if you're going to use a periodic table like this, the element, let me see if I can write here. Wait, can I write here? The element is in the position of the last electron. Okay, so what I did here is actually use this map on the periodic table, and what this does here, it helps you to see the element's energy level of that last electron. So what I mean by that is, I showed you guys this before, hydrogen actually belongs right here. And let me do this, let me actually pull, because I managed, after I showed this, I managed to actually find on the periodic table this right here. I think this is it. There's a lot of meaningful resources online, and there are really bad resources. So when we look at this right here, let me see, can I write on that? Oh no, okay. So you see where hydrogen is right here? The prefixes here, or the numbers, the whole numbers, 1, 2, 3, 4, 5, 6, 7. And you see how the color of the area here is blue? This area here houses electrons that live in the s orbital. Okay, so these electrons here tend to be the closest to the nucleus. And you can see right here, once again, you have the first electron right here where hydrogen is. The second electron will be where helium is. And for the hydrogen electron, this hydrogen electron is actually in the first energy level, and it's in a shape that's round. So using this information alone, I can actually draw out the orbital of the electron. So let me go ahead and pull this around here. So it's not meaningless, even though I'm just reviewing. Let me go ahead and let's see. So I'm going to go ahead and add a page here. So since we saw that for the symbol hydrogen, hydrogen had a label 1s. From here, we're getting information about two things. This one here tells you the energy level of the last electron in hydrogen. So you kind of need to bring in a lot of information, because you're asking, well, by the way, how many electrons does hydrogen have? So I'm going to pull this up, because I think they have the atomic number here. You see the atomic number here? This is 1. Hydrogen only has 1 electron. Okay? So all we're saying here is this 1 here represents the energy level of the last electron. Technically is the only electron in hydrogen. So let me try to draw the atom of hydrogen according to this symbol right here. According to this symbol right here, okay? 1 means you have a nucleus for hydrogen, and then you have, by the way, for this one here, I'm going to use Bohr's model. Let me scoot this to the bottom so I can see if you say anything. Feel free, by the way, to make comments, and that way, if I'm saying something, feel free to rephrase it your way, and then I can tell you if it works or not, because my other students do that in my other class. If I say something, the way they engage is by restating it differently in the chat, then I can go ahead and say, that's true, or I can correct it, okay? So feel free to do that. I have a nucleus here for hydrogen, because hydrogen only has, the 1 here just means there is 1 proton and 1 electron, right? That's what the 1 means. So this is my 1 proton right here. I'm going to draw the rest of the atom right here. And then I have 1 electron. So this is the atom of hydrogen. Based on this label 1s, 1 means even though you have many energy levels in here, 1, 2, okay, wait, I'll leave it as is. I'll just label this one here. Energy level 1, energy level 2, and then there's many of them in here. Let me say energy level 3. It's hard to draw these circles. That 1 electron is an energy level 1. So I'll go in here and place the electron right here. Hydrogen only has 1 electron and it's on energy level 1. So that's it. And then it says right here, it's 1s. What does the S stand for? We talked about S, P, D, F. The S is showing you the shape of the orbital where the electron lives. So this is showing you the shape of orbital. Okay? So we talked about that before. Once again, watch the previous video, but while we're here, the shape of the s orbital will be round. So over here, I actually have this correct. I have one electron on energy level 1, and the shape is round. Okay, so to kind of relate the two, let me skip over here and show you something in the P block. Let me look at boron to illustrate that. I'm going at this differently so you can understand the homework, because this chapter tends to be hard because people struggle to understand the concepts. So let's see, boron had what? 2p. Okay, 2p. So boron starts off with 5 electrons. And we're told boron is on the 2p level, according to this I had here, right? 2p level. So at some point, I did explain this later on, that the 2p level can handle a total of 6 electrons. But I'm trying to talk about the 5th electron in boron. So to illustrate that, I'll just show you here, 2p, once again. 2 stands for the energy level. That means the 5th electron in boron is on energy level 2 based on this number. The shape of the orbital is figure 8 based on this letter right here. So from the 2, I can tell the energy level. From the P, I can tell the shape of orbital. So if I were only to draw this, which you most likely would not be asked, but just for the sake of illustration, I will draw my nucleus in the middle, positive, and then find energy level 2. So the first energy level, the P is figure 8. This would be energy level 1 for figure 8. This will be energy level 2 for figure 8. And then somewhere in this, well, actually it's inside. So somewhere in here is my electron. Okay, they will not ask you to do this, but I'm trying to illustrate to you that these do have meanings, and they're telling you the energy level and the shape of the orbital. Okay, so as you go through, you see all that stuff. So what I'm going to do then, as I continue this, once again, I'm talking about what we talked about, the different information, but I'm approaching it from a very, very different level. So let me see. I did show you all of this, the shapes right here. The S shape is a sphere. P is figure 8. D, so it looks like each time the number of circles are doubling, right? S only has one circle as a sphere. P looks like figure 8, but in reality they draw it as 2 circles stuck together. D looks like cloverleaf. The common name is cloverleaf. Figure 8, the common name is dumbbell. But when they draw it, it looks more like 4 circles stuck together. And then F, I call it flower. When they draw it, it looks like 8 circles stuck together. So in the pictures that we're looking at here, if you ask me, it looks like each time the figure we're looking at is double. Like from here to here, it looks like it's times 2. From here to here, it's times 2. From here to here, it's times 2. So what Bohr said was there was a nucleus here, and then you had different electrons on different different energy levels. The quantum mechanical model says we wish it was that simple. Bohr only saw the sphere, only the circle. In reality, the space where the electrons live aren't always round like Bohr says. They have different shapes. So around the nucleus, I'm going to draw this here. Around the nucleus, the electrons, some of them live in a round shape. I'm going to use different colors to show the different shapes. Some electrons live in a shape that's figure 8. Some electrons live in a shape that's like this. Some electrons, let me see, what color should I use? Black. Only one that stands out. I use the black one. Some electrons around the nucleus live in a shape that looks like this. 1, 2, 3, 4, 5, 6, 7, 8. Okay? That's why when you look online, it just looks like a bunch of little bubbles in there. And these are all, and you have different levels of that. And all of these are inside the atom. Don't forget. So Bohr's version of what he saw was just the blue parts. You see the blue part here? That's what he saw over and over and over again. Scientists said no. There are actually four major shapes, and each shape gets bigger and bigger and bigger and bigger as you go through the energy levels. This one here gets bigger and bigger and bigger. This one here gets bigger, bigger and bigger. This one here gets bigger and bigger, and yeah, it gets complicated. You get what I'm saying? I'm showing, right? So versus having the simplistic view, simplistic one, you have one that's very complicated. Okay. Yes, each one gets bigger. Right. So remember the S, the P, the D, the F. Going back to that picture I was showing you here, this shows you where the electrons, so I call them the neighborhood because they're called blocks. You know, we call neighborhoods blocks. So if move helium over here, okay, so helium is neighboring hydrogen. This is hydrogen, this is helium. All the electrons of the elements right here, the last electron of the elements right here, they all live in the S block, the S neighborhood. So over here, these are all in the circular shape. So let me try to draw this from a, so energy level 1 will be a small circle, big circle, bigger circle, bigger circle, bigger circle, bigger circle. These are all S shaped. When you get to this one here, these are all figure 8. Figure 8, different orientation, figure 8, figure 8. And so with a figure 8, you have 3 different orientations. And so it goes into a bigger figure 8, a bigger figure 8, a bigger figure 8. Here you have the flat one, flat one, flat one, or the one that's lying horizontally. Here you have the vertical one, vertical one, vertical one. Now, I know I'm sharing a lot of details. All you have to remember is the S block has spherical shape. The P block, figure 8. The D block, they look like that. The F block looks like a flower. That's what you guys have to remember at your level. In the majors class, they have to know that there are 3 different kinds of P, and each one has a specific orientation. Now I show that. Right, they have exactly. Each one has their own hood. So my thing is like, yeah, the ones in the S block, they're all round. It's like going, you know how they build those houses in the neighborhood where every house looks the same? That's kind of like this one here. They're all round. Here they're mostly this shape. Here they're mostly this shape. Exactly. Here they're kind of the same shape, but they're facing different orientations, like that. You're getting what I'm saying? You should have been in the other session. The other ones, they don't say much, and so yeah, it's not bad. It's just it's more interesting when we're dialoguing back and forth. And then we went into the electronic configuration. So this is the part here. So up until this part before we get into sublevel, this I think was kind of the last lesson, where now you have to take on a different role. Once again, I'm bringing you into the lesson. You as a scientist, as a chemistry student, are now placing electrons in the different neighborhoods. So it kind of gets complicated here. You're placing electrons in the different neighborhoods. And so for that reason, the neighborhood analogy kind of doesn't work very well here. The neighborhood analogy only works better when you're dealing with individual electrons. When we're doing electronic configuration, for this one here, I like to use hotel rooms. I used to say dorms, but I realized a lot of community college students don't go to dorms, so they don't really understand what I'm talking about. So I like to use hotel rooms. I recently went to a hotel, and in the hotel, the same hotel had so many different buildings, right? So you have a building here, something like that, a building here, right? So this time, think of the analogy, okay, as this is a hotel. So let's switch from neighborhoods to a hotel room. And the hotel looks like this. And what you're doing though, I try to flip this here, but it's hard to flip it. It's not really even flipping. But think of it as, because it flipped on my screen, but not on you guys' screen. You have a hotel, and what you're doing here is placing residents inside the hotel. The residents are going to be your electrons, and you're placing them in rooms. The rooms are going to be orbitals. Okay, so I'm using an analogy here. And then you're going to have floors. The floor will be an energy level. So let me actually add this down here to see. You're really getting my analogy, so it's making me easier for me to go through this real quick. So once again, back here, electrons are the residents of the hotel. Then we have the rooms. Sorry, this is the left part should be the chemistry. So the rooms will be on the right. The rooms are the orbital. And then the floor will be the energy level. I should say, the sections in the hotel, do they call those wings? Is that what they call those? Do those sections, like, even on the same floor, you have different kinds of rooms? Because on my floor, I saw this door one time, and the door didn't have other doors next to it. So then I realized that might be like the penthouse. It was a lot bigger. So let's say wings. The wings will be the sub level. These are sections on the same floor. And then the floor of the hotel will be the energy level. So I'm using something that hopefully we can relate to talk about the chemistry. Okay? So quantum mechanical model focuses on this left part. We want to know a lot about the electron. We want to know how, first of all, where the electron is. We want to know what orbital it is in. We want to know what sublevel it is in. We want to know what energy level. Okay? So for this one here, the energy levels go with these numbers here. So you can tell here energy level 1, 2, 3, 4, 5, 6, 7, as listed, right? Here in the 2p level, technically this belongs here. So 2p level, this section here is empty. There's nothing here. It starts off with 2p, 3p, 4p, 5p, 6p, 7p. So here, the lowest level on here is 2, 3, 4, 5, 6, 7. On the D level of this hotel, the D wing, we have 3, 4, 5, 6. And the D wing is missing a 2 and a 1. So please notice the D is missing energy level 2 and 1. Okay? And then we have this other wing that looks like an afterthought for our periodic table hotel. Okay? It looks like an afterthought, but technically, when it comes to assigning the electrons, we will place this right here. So when you get to 6s, we will detour down to this other wing that's not attached to the main hotel, go all the way here, and then come back and then continue here. So I'll show that to you when we're going to the configuration. And so I think I've done all the parts. So the role here is to place the electrons for the different elements based on the room position, the wing, and the floor. So I've shown you what floors we have here. So on this one here, on this detached part, we don't have floor 1, 2, 3. It starts with floor 4 and floor 5. Okay? The way we do this is there are rules. According to a scientist, that was Pauli's exclusion principle says when you're dealing with electrons, you can have in the rooms or the orbitals, you can have a maximum of 2 electrons per orbital. Okay, a maximum of 2 electrons per orbital. It would be like saying a maximum of 2 people per room. So 2 residents maximum per room. The room can be empty. It can have 1 person or it can have 2 people. Okay? And then the wings we're working with, we have these 4 wings, these 4 categories. The S wing, the P wing, the D wing, the F wing. When we are filling the electrons in here, another scientist called Aufbau said, start with the lowest energy first, lowest energy orbital, then go to the higher energy. In other words, as you're placing the residents in the room, start from left to right, then go from left to right, from left to right, from left to right, from left to right. And we'll practice that so you can see. Okay, I am trying to give you the Cliff Note version, the best I can do considering. So we'll be placing electrons inside the rooms, going from left to right to make sure that all the electrons in the orbitals have been placed. And then we'll start looking at the electrons based on the sublevel. So let me go ahead and practice this versus talking about the rules anymore. Okay. So for this part, let me check real quick. At some point, I did bring in the better periodic table. If not, I really thought I did. Oh, here it is. It makes it so much easier at this point for me to use this periodic table. So let me use this because it's a lot easier, like I said. We're going to use the electrons in here, and we're going to be doing the electronic configuration. So the rule is this. In the configuration, we are actually placing electrons per sublevel. So what I mean by that is each sublevel is like each wing on the floor is a sublevel. Like 1s, if I move this over, 1s can handle a maximum of 2 electrons. Using the periodic table, how can you tell the number of electrons? You want to actually block you want to section out the periodic table in 2 columns. Each of these columns here give you 1 room or 1 orbital. Okay, so this is 1 orbital, another orbital right here. So I'm sectioning these out so you can see. And as I block out 2 electrons, those 2 electrons or 2 elements become roommates in the same room. So hydrogen and helium room together. And then over here, boron and carbon room together, nitrogen and oxygen room together, fluorine and neon room together. Going down here, same thing. These 2 room together, they room together, they room together. They room together, they room together, they room together. Okay? So I'm going to show you this so you can see how it works. Just go down the group and group them in 2s. In the D block, same thing. These 2 room together, they room together, they room together, they room together, they room together. And then within the room, please notice there are going to be 2 electrons possible. So the first one I'm going to draw using the up arrow. Second one, I'm going to use the down arrow. Now, I think with the others, I don't think I went this detailed. I'm trying to make sure I'm not going to the majors level. So all I'm going to say to make sure it's not complicated is I'm just using these arrows to keep track of the electrons. First electron, second electron, first, second, and you can go through and label that like that, first, second. You don't have to use that because at you guys' level, all we're trying to figure out is how many electrons get placed in that level, in that wing, okay? So if you want, you can go through and put all that in. If that's confusing, don't worry about that. I'm going to try to do it without that because your book doesn't go in that much detail. Okay, so let me start with hydrogen. Hydrogen has 1 electron. So back to the beginning. Hydrogen has 1 electron, right? And the question is, what sublevel? The sublevels are these small levels here in yellow. Is that 1 electron located in? So you can see where hydrogen is. I'm going to use a highlighter. Hydrogen is right here. Hydrogen has 1 electron. The 1 electron lives in the 1s sublevel, and you place it like this. So this part here, highlighted in yellow, is the sublevel, the wing of the hotel, and it shows you up here how many electrons you're going to place in the 1s sublevel, in that wing of the hotel. Since hydrogen has got 1 electron, you will place the 1 electron right here in the 1s sublevel, and that's it. And this is called the electronic configuration of hydrogen. Okay, hydrogen has 1 electron. Where do you place it? In the 1s sublevel. How many do you place there? Just the 1 electron it has. So I'm going to go in order, and hopefully as I go in order, you see how it works out. Okay, because I mean, once again, I'm kind of condensing it. The next one will be helium. Helium is a neighbor to hydrogen, right? Remember, the helium element is listed on the 1s sublevel. Helium has 2 electrons, okay? I mentioned here the 1s sublevel can handle up to 2 electrons based on the number of boxes, right? It can handle up to 2 electrons. So helium has a total of 2 electrons. Where do I place both electrons? Both electrons for helium are placed on the 1s sublevel. Why did I pick 1s? Because of this label one here, right here, this section here is called 1s. So you place both electrons up here because both electrons from helium are placed on the 1s sublevel. Okay? Please notice where hydrogen is the position of the first electron. Where helium is the position of the second electron. So both electrons are on the 1s wing of the hotel. Okay? So let's go ahead and move on. Let's spread this out a little bit. We're looking at lithium. Lithium has 3 electrons. Okay? Lithium is right here. Remember I mentioned this earlier, and it's going to all kind of come together as I go on. Lithium has 3 electrons, but lithium occupies the position of the last electron, not all 3 electrons. That means if you look at where lithium is on the 2s level, right? So lithium is showing you where electron number 3 is. But lithium has 3 electrons. So we have to place the first 2 electrons and then place the third electrons. The first 2 electrons occupy this part of the hotel, this wing. What is that called? It's called 1s. So place the first 2 electrons in the 1s sublevel, and that's where they are. The third electron goes where lithium is. What is that part called? It's called the 2s sublevel. How many do I place there? The remaining 1 electron. Okay, so I'm going to keep going for a little while, and then hopefully I'm going to bring you in. So next, beryllium. Beryllium has got 4 electrons. Remember, the first 2 electrons occupy this position here, where hydrogen and helium are. So the first 2 have to go in 1s2. Beryllium is on the position of the 4th electron. Lithium is on the position of the 3rd electron. So the 3rd and 4th electron are roommates, and they together stay in the 2s wing of our quote-unquote hotel. Okay, so the 2s sublevel has 2 boxes, therefore it can handle 2 electrons. Each box goes with 1 electron. So it's kind of like a puzzle, right? So I'm going to build up now. I'm going to bring in boron. No, this is just boron, not beryllium. Boron. Boron right here. Boron has got 5 electrons. Please notice, all first 2 electrons have to occupy this position, regardless of the element. What I mean by that is, the first 2 electrons for boron will be placed where hydrogen and helium are. So they'll go here. 1 is 2. Electron 3 and 4 will be placed where lithium and beryllium are. So that's going to be called 2s2. But we still have the 5th electron. So can you tell me how I'm label the sublevel here for the 5th electron? Where boron is? Have you figured out the trend yet? Can you tell what sublevel boron is in? It's labeled right here in yellow. So this is going to be 2p. Okay, and since we have just 1 electron left, it's going to be 2p1. Okay, So let's see if we can do it for carbon together. Carbon has 6 electrons total. With carbon, the first 2 electrons have to go here because all first 2 electrons have to go right here. So right here I have 1s2, and over here I have 2s2. And then I have, for carbon, let me see, I have 2p2. So once again, as you are placing the electrons on these sublevels, the different wings of the quote-unquote hotel, you want to make sure you are being consistent, okay? Okay, let me see. So you go ahead and do, can you guess what nitrogen is going to be? Nitrogen has got 7 electrons. Can you guess what the configuration for nitrogen will be? Following the trend we have here. So by the way, oh, that's okay. By the way, when you try to figure out how many electrons that sublevel can handle, just count the boxes in the periodic table. This level here, the 2p level, can handle 1, 2, 3, 4, 5, 6. It can go up to 6 electrons. So let's go ahead and try the one for nitrogen. We did boron, right? We did carbon. Now we're gonna do nitrogen. Where do I write that? I'm running out of space. So let me write it up here because I want to see the periodic table. So the boron had 5 electrons. It was 1s2, 2s2, 2p1. Carbon has 6 electrons, 1s2, 2s2, 2p2. Now we're dealing with 7 electrons from nitrogen. So you see the trend, right? And then of course you can see 2p1 goes with this position, 2p2 goes with this position. So what will the full configuration be for nitrogen? So it's kind of like a puzzle. Okay, yeah, let me know when you got it. Now, mind you, you're getting the Cliff Note version. So once you go through the lesson, in detail, it will be a lot easier for you because I'm kind of throwing you in the deep end, but it will make things a lot easier for you. And people usually struggle with this part here, but that's just because it does require a little bit more investment and a little bit more time. So see the trend, right? One is, yes, exactly. Because this position here, this whole wing is 2p. Everything in here is labeled 2p. Boron is 2p1. This is 2p2. This is 2p3. So this position here with oxygen is 2p4. Here, fluorine 2p5. Neon 2p6. Right. So essentially, the last part changes. 1s2, 2s2, 2p3. So if you did oxygen, it will end with 2p4. Fluorine, 2p5. Okay, you're getting it. Very good. Very good. Mind you, this is a Cliff Note version. Still go watch the long one so you can get everything because the questions in the homework do get into details. So yeah, very good. Okay, so now let's do one that's a bit more complicated. Let's do AS. So AS is a cousin of nitrogen in the same group, right? So we'll do AS. We have to fill the electrons from the beginning to where AS is. So let me go ahead and do it this way. AS starts with 13 electrons. The other thing I want to mention, sorry, not 13, 33 electrons. When you add the superscript, they all have to add up to the number of electrons you started off with. So remember, helium is here, right? Taking care of the second electron. So we're going to keep going until we get to this position here, then we'll stop. We'll assign the configuration until we get to the 33rd position where AS is, and we'll stop right there. Okay, so we're going to start from left to right. These two, from here to here, 1s takes care of the first 2 electrons, right? Remove this from here. From lithium to beryllium, handles this 2s level, handles electron 3 and 4. That's 2 electrons, all the 33. From boron all the way to neon, handles 6 electrons. 1, 2, 3, 4, 5, 6. Yep, that level is called 2p, handles 6 electrons, right? From sodium to magnesium, we're talking what? That's 3s level. That handles 2 electrons. Remember, each box is 1 electron. Then from aluminum all the way to argon, that's level 3p, handles 6 electrons, right? Oh, sorry, I made a mistake. Oh my goodness, I made a fatal mistake. Not fatal, nobody died. I made a gross. No, I think I'm fine. I'm from here to. Okay, sorry, I don't know what I was thinking. I thought I made a mistake. We're going all the way to 33. We're not there yet. 3p6. I'm fine. I'm fine. Woo! Okay, for a moment there, I panicked. I am now at argon, right? And instead of me panicking, I know better. I shouldn't have panicked. I can just check. 2 plus 2 plus 2, that's 10 right here. 2 plus 6, 8. So I have already placed 18 electrons, right? So I'm nowhere near the end. I thought I skipped something. Okay, so here is, when I'm here, I've placed 18 electrons. I have to go through energy level 4. Okay, so what comes next? Let me make this smaller. Okay, after 3p6, now I'm at potassium to calcium. Oops, right here. This takes care of electron 19 and 20. That's going to be level 4, let's see, level 4s. And that has 2 electrons, right? Then when I go here, this level is called 3D. Go by the label of the name. So level 3D, since I'm going all the way to 33, level 3D takes care of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The D sub-level can handle a maximum of 10 electrons. So that advances me from 21st electron all the way to the 30th electron. Okay? And then I said stop at 33, right? So now I have to go from 31 to 33. This level is called what? Let me erase this so I can see. It's called 4p. So in the 4p sub-level, I'm only going to go up to 3 spaces. That's where AS is, so 3. And this is called electronic configuration. So when you add this from here to here, here's got 10, 2 plus 6 plus 2, another 10, 10 plus 3, 13. Yep. If you add superscripts, you get 33. So we have 33 electrons. Okay. Electronic configuration. Not bad, right? Because essentially, after I did all this is kind of, yeah, what we're doing with the other people. So let's do a more complex one, just to make sure. I'll do palladium. No, let's do platinum. People are like, oh, platinum will be complex. I think you can handle it. This is a review, by the way. I'm not even doing this for the first time. So let's do platinum up here. People talk about platinum. White gold is so last year. Let's do platinum. So we'll do platinum. Platinum is right here. Platinum has how many electrons to place? 78. That's a lot. Okay. The first 2 go here. 1s2. The next 2 go here. 2s2. Then from here we go to here. 2p6. So now I'm just maxing everything out. I'm maxing everything out until I get to the D block, right? This part here. Then I'll slow down. So I'm at 2p6. From here to here, 3s2. From here to here, 3p6. From here to here, 4s2. Here to here, 3d10. So I'm going all the way here, right? From here to here, 4p6. I keep going. From here to here, 5s2. From here all the way to here. It's a lot of writing here. This is 4D. Let me erase all that. So my stopping point will be where platinum is, right here. Okay. So from here to here, I'm like 4D. So 5s2, 4D10. 4D10. It's made it here. From here to here, I can continue down here, 5P6, right? Then now I can slow down. From here to here, 6, I'll write it down here, 6s2. So I have 5P6. I'm here, 6s2. Now remember, I have to, this is a, I have to detour right here. You don't write this one here. You have to detour right here. So I'm at 6s2. I detour here, and this level is called 4f. 4f. Since I have to go all the way to the end, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The 4f takes care of 14 electrons all the way to the end. Then I come back here where lanthanide is. So I go all the way back here like a detour and continue from here. From here to here, oh, that's where platinum is, right? This level is called 5D, and I go 1, 2, 3, 4, 5, 6, 7, 8. 5D8. How was that? That was a tough one, right? That was a tough one, but my purpose there was just to show you you're reading from left to right. Don't forget to move, I don't say what's his name. Don't forget to move helium over here, because in this context here, helium rooms with hydrogen. Okay? So they go through the long version of it. So what we did here, I did some tough ones with you because you can handle it. Now you have the rest of the time to go through this step by step. I want to talk about the shorthand, and I think the rest of it you can watch the video on how to do the, what is it called? How to do the valence electrons and this one here, because I don't think that part is hard. You can do that by yourself. And the Lewis symbols, you can do that part by yourself. Yeah. So the part I want to go over with you is just the shorthand. That part is tough too. It shouldn't really be tough. But chemists get lazy. I wouldn't say it's lazy. They get tired. When they get tired, they're like, we don't want to write this whole configuration. Like this one here, platinum. Platinum was a lot. 78 electrons. Can we do a shortcut? Yes. So let's do a shortcut. Well, how do you do a shortcut? They decided to select group 8. Group 8 are these right here. And use them as a shortcut. So with platinum, what we're going to do here to show you how it's a shortcut, platinum has 78 electrons. So from here, oh, well, it's about to anyway. I'll do a couple of homework questions with you since you showed up. Platinum is in group A. So you want to, sorry, is in the D block. You want to go to group 8 and find a group 8 element that has electrons close to 78. So remember, platinum has 78 electrons. So we have xenon, and then we have radon. Radon is too high. So write xenon, Xe, in brackets like this. Xenon has 54 electrons, so you write 54 here. All this means is, don't start from the beginning. Start from where xenon is, and then go from here all the way to where platinum is. Because xenon, the symbol, handles or takes care of 54 electrons. So from here, continue. After xenon, go here, 6s, 6s2. Go down here, 4f14, 4f14. Go back up here, 5d, 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6, 7, 8. 5d8. So with the shorthand configuration, you don't start from the beginning. Start from either neon, argon, it could be helium. Start from helium, neon, argon, krypton, xenon, and go all the way to the end. Okay? Yeah, I know it's a lot. So for the part here I never got to, which is okay. This part here is just asking you about the characteristics. So I went through all the parts that have marks. I went over that in the chapter. This part here is just showing you, let's see, the part that I didn't go over. Oh, the metallic character, where the metals are, non-metals. It's easy to figure out. All of these are metals in the periodic table. These are non-metals. These parts here, the elements over here, have both metallic and non-metallic behavior because they're metalloids. So if you're asked which one is a metal, non-metal, just go ahead and use this picture here to compare with the elements. Make sure you know the properties of metals and non-metals. Yeah, pretty much that's what's showing over here. And so what I'm going to do right now, and this is just showing you how metallic behavior increases. Both of your metals are to, not both, most of your metals are to the left of the periodic table, right? Just use this picture, it's a lot easier. I want to go ahead and apply some of this stuff because you took in a lot of information. Let's go to, oh, this logged me out. Let's go to the homework. And I will post the links once we're done. Where's the homework? Oh, right here. So I'm going to skim over some of the questions we talked about today. Okay. Okay, assignments. So this is chapter 11, right? Yes, I'll view it as a student. Okay. So this is stuff that I didn't really cover in detail today. I talked a little bit about that, but let me see. Not today. Oh, we can look at this one, okay? Because we discussed this today. This is Niels Bohr when he was younger. Just telling you, in the Bohr's model of the hydrogen atom, the electron occupies distinct energy levels, and they show them to you right here: energy level 1, 2, 3, 4, all the way to infinity. One transition between energy states of the hydrogen atom is presented by the picture on the left. So you can see this is the home state, and it's going to an excited state right here. In this transition, an electron moves from what level to what level? What should I put here? Okay, one, whoops, one, and then here to what level? 3, yeah. And then it says here, energy is, oh, for it to go from 1 to 3, what is happening? Is energy being absorbed or is it being emitted? Emitted means being given off in the process. Okay, very good. I guess I type A here. Do I type the whole word? We'll find out. Let me see. Oh, they allow you. Okay, I just put A and see if A works. And then the electron moves. Okay, yeah. So as the electron is going to a high energy level, you see how all the details are missing here? Is the electron moving closer to the nucleus or further from the nucleus? Remember the picture I had earlier? Is energy level 3 further away from the nucleus or closer to the nucleus? Remember, the nucleus is going to be, exactly, the nucleus will be down here. So I guess I'll put B here. They didn't really say. Let me try. Yes! I shouldn't be excited, right? But this is so affirming, those little green check marks right there. But yeah, so you see, even though I kind of skimmed over it, that's why I gave you guys the extra stuff. Because you can see right here in this question, they didn't tell you about the nuclear position. That wasn't even clear in the lecture, right? But then once you go through and you give the answer, they tell you, yeah, this is right. Wait, there's more? Let's see what they have next. Oh, seriously? Okay, you can do that one, right? Going from that energy level. Now it's on its way back. So it's the reverse. Okay, seriously. Okay, I put here 3 going back to 1. The energy this time is being emitted, right? Because it's being given off. Oops, what is this symbol? Shift B. And then the electron moves closer to the nucleus, so it's going to be A. Let me see what happens. Submit answer. Yay! Okay. Yeah, so this one here, let me see. When you're working on these, you only need to work two to get mastery. You're working to get this right here. So you have a choice if you want to work the third one. You don't have to though, because once you get this is like a seal of mastery. You're good. You can move on. I don't know if you guys knew that. And this is showing the different shapes, right? The orbitals are S orbitals are spherical, P orbitals are figure eight, D orbitals are clover leaf, and then they show you that as you go from one energy level to another bigger energy level, the shape each shape gets bigger. So it's kind of reviewing everything I said. Oh, maybe we can do this. Okay. Which one will you match the first one with? What letter? So you see, the questions are not that bad. Yeah. So this is how you match. You drag it here. Oh, wait. Click. Oh, okay. Click, click. What about this one here with four, looks like a clover leaf? And the quantum part, yeah. So let me see. Click here, click here. Yeah, then that means this goes with here. P. Submit answer. Yep. And they go tell you da 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 whatever, whatever. Yeah, so it's but if you don't understand what you're doing, then it makes it really complicated. So yeah, once you go through this, then this stuff I really explained a lot last time, but based on what we did today, all the S's maxed out at 2, all the P's maxed out at 6, all the D's maxed out at 10, all the F's maxed out at 14. So as you go through here, you'll be able to work on all of these. We did the configuration, you saw that, right? So they show you how you're detouring here. Yeah. So the most concerning part, we already did that. Here they have you write the complete configuration, and then for here you're doing the noble gas for nickel. Trying to see what else you do. Yeah, the rest of this is really not that this part here. I went over it already last week, but these dots go with the group numbers. So it's like what group one, and this is one dot, group two, two dots, group three, three dots. So just go through it, take notes as you prepare for the exam, and then yeah. The rest of this I would say is easier because there's not a lot of mystery there. Once you go through the notes, you can work on this. So my suggestion for you is go in order like I did right now, right? I am only answering questions based on what we covered today. I'm not trying out questions we haven't covered. I actually suggest that's how you do all of chemistry. Don't When I was doing homework as a student, I didn't cover the whole chapter and do my homework. Never. I did a small section, did the homework, and as I understood that, well, then I moved on. And so I was diligent to do the homework all the time. I mean, if I really knew it, I did the whole thing. If I didn't know what I was doing, I do a small section like we did today, quantum mechanical model, and do all the questions based on what I just covered. And a different day, do a different part, do all the questions on that. Then for the exam, I review everything. Then I kind of have a bigger picture. And that helps you versus having just one day for the homework. To me, that's overwhelming. Okay. But yeah, I feel like we went over the hardest part. The rest of it is a lot, even though it may look complicated. Ooh, I like the little M thing. I can't work it. I have to work. But even though it looks complicated, once you go through the lesson from the first chapter, sorry, part one of chapter 11, this one here will make more sense as you go through. It will make sense. And going through all this will make more sense. Any questions? Okay, you're welcome. And I'll go ahead and post these since I forgot to do that. I've been super busy with meetings and my other class. There's a lot of changes going on behind the scenes. So yeah, I'll be sure to go ahead and post this. But all the best on your exam. Take good notes because when you take good notes, it makes things easier. Highlight words, terminology. Make sure you know what these words mean, right? That way, when you're reading the text in the exam, you're not spending half the time trying to figure out what does this word mean. Okay? Terms like orbital, stuff like that, make sure. Okay, great. You should be good. Okay, have a nice weekend. I'll see you next time. Okay, thank you.